What's up, everybody? Happy Tuesday. You should be watching this on Tuesday. So yesterday, first video, we started to look at how to create a t-interval to estimate a population mean based on a sample mean. And to kind of procedurally get through that using our graphing calculator, right, very doable for us. But it raised this question we saw with the formula, right? We had the critical value was a t-star, right? So we're not working with the normal model anymore. We're not working with z-scores. Now we're working with something called the t-distribution. And just as a side note, just so you know, a z and t-score, those were both a standardized test statistics. So the way a t-score is calculated is the same as a z-score, so no big deal there. But it's a different distribution. And so today, we want to talk a little bit about what the t-distribution is, how it's different, and then we're going to look at how that connects to our p-values for our hypothesis tests and our critical values for our confidence intervals. So here we go. Let's jump in. That's a t-table. We got that. Remember, we only cared about the bottom row for our z-stars. Today, we're going to start to use the rest of it. But anyways, here we are. So we're talking confidence intervals, hypothesis test, or mean still the same chapter, but now we want to focus just on this t-distribution thing. So I'll tell you over here in this picture to the right, you can really kind of deduce some things yourself. If I tell you that the blue is a normal model and the red is a t-distribution, you can see how those things compare, right? Pretty similar in terms of their shape, but there are some differences. So the t-distribution, it's called student's t. The t-distribution was developed by a statistician named William Gossett. And William Gossett worked for the Guinness Brewery. He was the quality control engineer. I think that just means like taste tester, but it sounds fancier. But he was also like a math genius, obviously. So and if we were in class, I'd tell more about the story, but so he was doing some work with his, with ensuring the quality of Guinness Stout. And he noticed that type 1 errors were happening too often. He was using an alpha level of 5%, but was seeing 15%, or seeing type 1 errors 15% of the time. So he knew those things didn't jive, right? Because alpha is supposed to be the probability of type 1. So like any reasonable person, he was like, yo, normal model's not working. I'll just invent my own statistical distribution, t-distribution. Couldn't put his name on it though, because Guinness was super secretive about their formulas for their beer. So he had to publish it under the pseudonym, and he chose just Student's T. Nonetheless, so right, this is really just like a bunch of information we have to know. So this year, I'd be surprised if this was on our exam because it's more information recall, but it's stuff we need to know. So the student's t-distribution. First off, the t-distribution is a family of distributions. So the t-distribution is not one curve. Like the normal model is one curve. It always looks the same, right? It's that bell curve most of us picture. So the t-distribution, its shape varies, right? So it's a family of distributions, and its shape varies based on something called degrees of freedom. Now, before we get into that, it is, as we saw in the title slide there, it is unimodal and symmetric. The key difference is that it has like fatter tails. So for example, like if I were going to draw a normal model, maybe I'd do something like that, and forgive my drawing here because I am using a mouse. A t-distribution is going to have more variability. It's going to be a little more spread out, and it's going to have like fatter tails. Notice, right, the tails here on the right side, right, there's a little more width there as compared to the normal model. So that's what I mean by wider or flatter or fatter tails, however you want to say it. So the shape depends on degrees of freedom. So degrees of freedom are calculated n-1. Ignore this little a, that was supposed to be an arrow. But anyways, so degrees of freedom, n-1. So sample size goes up, degrees of freedom goes up. And here's how it works. The shape of the normal distribution, I'm sorry, take that back. I didn't say that. Delete. The shape of the t-distribution varies based on those degrees of freedom. As the degrees of freedom, as the sample size increases, our shape gets more approximately normal. So the larger the sample size, the more our curve starts to, the tails kind of go down and match that black normal model. Or in other words, as the sample size, as the degrees of freedom increase, our curve is less spread out, right? It kind of more mirrors that normal model. On the other hand, if we have a smaller sample size and we have lower degrees of freedom, then our curve gets more spread, the tails get a little fatter, and there's more variability. So bigger sample size, more degrees of freedom, less variability, more like a normal model. Smaller sample size, lower degrees of freedom, fatter tails, more variability, a little more spread out. what I'm doing with my hands is meaningless at this point. I'll just go to the next slide. So think about this. Let's say that these three curves, green, red, and blue here, all represent a t-distribution. So 4 questions. A little review here, nothing new, just which one's got the most variability, which one's got the least variability. And then based on what we just saw, which color would be based on the largest sample size, highest degrees of freedom, right? Those kind of go hand in hand, which would be based on the smallest end. So give it a pause, think about that. And hopefully you told me most variability, most spread out, that's our fattest tails. That's gonna be the red here, right? It's a little more stretched out. So most variability is gonna be red. Least variability, that's gonna have like the skinniest tails, I guess. And that's what we see here with the blue. That's most like the normal model. All right, so if I was gonna pick one of these to be a normal model, it would be the blue. So the largest sample size, that's the least variability. The bigger the sample size, the closer the t looks to a normal distribution. Notice if you look at your t-table, when we would look up the confidence levels for the normal model, it was that bottom row, right above the 95, 98, whatever percent confidence. And to the left, you would see the degrees of freedom listed as infinity. So a normal model is theoretically a t-distribution with infinite degrees of freedom, whatever that means. And then lastly, the smallest sample size. This would have the smallest degrees of freedom and thus the most variability, and that's going to be our red, and green would be in the middle. This might be a question that makes us think a little more. This would be typically in the past years a multiple choice on the AP exam, something like this. And we'll see some of that in our classwork throughout the week. So let's talk about the critical values, the Z star versus the T star, right? So normal model, 1 prop Z, 2 prop Z, right? Z star. T-distribution, means, mostly, we'll touch on that. T-distribution though, talking T-stars. So we need to know how they compare, and then we need to know how to actually find them. We'll assume n equals 30 because we do need a sample size for degrees of freedom, and we'll look at those in 2 ways. So first up, let's jump here. So the critical value. That's our Z star, that's our T star. And recall that the critical value is like the number of standard deviations away from the mean of a sampling distribution for a given confidence level. So the critical value is, for instance, let's say this black curve is a normal model, right? So Z and normal model are synonymous. The critical value is, it's a pretty bad normal model. It's bothering me enough to the extent that I'm gonna probably redraw it equally badly. A little better. Anyways, so the critical value is, like, if I wanna contain, let's say I wanna contain 95% of the data, it's how many standard deviations do I have to move to the left and to the right? And if we even recall back to the empirical rule with the 68, 95, 99.7 rule, right? We know roughly for the normal model, roughly 95% of the data is within 2-ish standard deviations. But then as we got a little later into this, we learned that this was 1.96 and negative 1.96. So the Z-scores of negative 1.96 and 1.96 would contain 95% of the data. But for a t-distribution, here, oops, sorry about that. Since the t-distribution has fatter tails, so let's look at, like for the normal model, this green area, right, is about 2.5%, and this green area is 2.5%, right? 95% in the middle, leaves 5 for the outsides, cut it in half. For the t-distribution, and I'll draw an extreme version of this, we're gonna have fatter tails. So if I mark the same spot from here to the right, I'm sorry, from here to the left and from here to the right, like this, below this blue curve, right, there's more than 2.5%, right? Like this blue slashed area is bigger than that sloppy green shaded area. Or over here, this blue slashed area is bigger than that green shaded area. So that means there's more for the blue, for the t distribution, there's more than 2.5% of data outside 1.96. So for a t distribution, again, kind of extreme with the tails there. For a normal model, the t, fix that, sorry. Since this is more stretched out, if you imagine grabbing this black curve and stretching it out, that's not going to make the peak of this curve higher, that's going to make it lower. So to make my picture better, maybe something like that. So here, right, like these spots, negative 1.96 and 1.96, that contains 95% of the data here in black. But for the blue curve, from here and here, right, like inside here in the blue curve, this would be less than 95% of the data because there's more on the outsides or maybe because the top's lower. So in order for me to contain 95% of the data, I'm going to have to move further out. Right, so my critical value for T star is going to be larger, further away from the middle for the T distribution than for the normal model. Literally picture taking this black and stretching it out. So these two black lines that I have move further away. That pretty much just makes everything I just said irrelevant. All right, so how do we get T star? This will actually give us some insight. We know for Z star, for instance, for a 95% confident, a 90% confidence level, we know that this is 1.96. What am I doing? We know this is 1.645. Let's look at a different way we can get that. What I can think about here is for the normal model, and I say normal model because I'm under Z star, we want 90% of the data to be between this Z star and this Z star, the positive and the negative. Sure, I could look that up in the table, or think about this. If we're given a percentage and we want to go back to a Z-score, a little review for us, this is an inverse norm opportunity. So what I could do over here is like for this spot, inverse norm, my area is the percent to the left, and that's going to be 0.05, right? 90% in the middle leaves 5%, or 10% for the outsides cut in half. And then my mu is going to be 0, and my sigma is going to be 1 because we want everything in terms of Z-scores. And if I do that, I'm going to get negative 1.645. Or for this side, my area to the left would be 0.95. And so I could change this to 0.95. And if I do that, I'm just going to get positive 1.645. Or if I have a newer TI model, I could even enter, I have my tail option. So I can choose for the tail, the center. And then for my area, I can put the area that's in the center, 0.9. And it'll give me both positive and negative 1.645. Or just look it up in the table. But that's one way to get those values. So for T star, not all the degrees of freedom are listed in the table. And remember, we're assuming n equals 30 just because I said so, because we need an n. So for here, same idea, a little bit fatter of tails, right? This is our T distribution. So we want 90%. So we can do the same thing. But now, instead of inverse norm, we're going to use inverse T because we're talking T distribution. My area is always to the left. So to the left of this, again, would be 5%. So I could do 0.05, comma. Now I need my degrees of freedom, which are n minus 1, so 29. And that's one way to get my T star. Or I could do inverse T 0.95 and 29, and that would be focusing on this spot right here. So that's one way to get your critical values. However, I'm pretty confident that if you have a TI-83 calculator, that is not an option. So there's got to be another way. You know, I like to start with the harder, like the more complicated, the thinking way first. If I show you the easy, mindless way, then you won't listen to the hard way. So let's see what our other option is. I challenge you to think about what those critical values would be for a sample size of 30 for 99%, but in the interest of saving time in the video, I'm going to hold off on that. So here's your other option, like the one that you're probably actually going to do. Although I suppose this year it's a little weird because you, again, won't be given a formula sheet and t-tables and all that. There is a t-table in your textbook you could reference in the back of the book. You could print one, have one open, like whatever works for you. But our other option is to just use the table. So we got these t-tables, right? Previously, when we were doing our 1 prop, 2 prop z stuff, we only used these bottom numbers. For us, that wasn't listed as a z. As I mentioned earlier, for us, this row is listed as an infinity symbol, right? But there's my 1.645. So to get a t star, right? So those are all z stars there in red. To get my t star, it's like the same kind of idea. This dotted line is just here because this is showing a break, right? Like you can see it goes from 5 to 24, and I'm just gonna not make it red since I just said red was all the z stars. But here, to get a t star, what I can do is I just look up the degrees of freedom and my confidence level and see where those meet. So we're talking 90% confidence. We have 29 degrees of freedom, right? Boom, see where those meet. So there's my critical value. So going back to yesterday's video, this is how I could get that t star for the confidence interval formula. And you'll see a multiple choice, at least in your assignment, where you have to choose the correct interval formula. So you'll have to be able to look up t star. You have a couple other questions that ask you to do it. So you can use the table, or you can use inverse t on your calculator if that's an option. One thing, the table doesn't have every single degrees of freedom ever. So if you were in a situation where the degrees of freedom were not listed down the left side, then inverse t becomes your only option. On the exam, I don't think that's going to happen, because if you have a TI-83, you can't use inverse t. So if it weren't in the table, there'd be no way for you to find it. So that's that. Now let's talk about p-values. So working with our normal distribution, kind of moving away from confidence intervals. P-value, right? We know a p-value. Sorry, let me just jump ahead right here. We know a p-value. We're like thinking about the amount of space in the tail. So we're looking at a t-score of 1.456 with n is 50. And we're talking about an alternative of greater than, right? So this is all important information. We got our t-score, sample size, and that tells us what our alternative is. And then we're going to want to look at what happens if we have a t-score of negative 2.5, n is 50 again, but now our alternative is not equal to, because we're talking about a statistical difference. So to do this, no big deal. This shouldn't be that big of a deal, right? We had some questions in class where I would say the z-score for a test was 1.456. The alternative was for an increase, so greater than, so we knew we were shading to the right. And I asked you guys, how could you get the p-value? We had multiple choice about that. No big deal. You told me normal CDF, 1.456, infinity, 0, 1, and these were zeros and ones because we were talking about z-scores, right? No big deal. So with the t distribution, it's like the same thing. The only difference is, instead of using normal CDF, when you press second vars on your calculator, I'm sure you notice, now we're talking about t-CDF. So I'm going to make these tails a little bit fatter, but the idea is still the same. So here's our t-score of 1.456, something like that. Shade to the right. I know I'm shading to the right because the alternative was for an increase or greater than. And so I'm going to go t-CDF. All right, so on my calculator, I'm just going to pop second vars. You can see there's a t-CDF. Mine's number 6. There's that inverse ti reference, number 4. Same idea. It's lower, upper. We don't need the 0 and 1. We just need our degrees of freedom, right? So now my lower and upper are the same things. 1.456 infinity, right? Lower is how far left is this shaded region. Upper is how far right. And then my degrees of freedom would be 49. So we're going lower, upper, DF. If you have an older calculator, you got to know what to type in, lower, upper degrees of freedom. And then when I press enter there, whoops, 4, 5, 6, bunch of 9s, 49 degrees of freedom. Boom, there's my p-value. Now, when we do the actual t-test on the calculator, we won't need t-CDF, just like when we did a 1-prop z-test, 2-prop z-test, we didn't need normal CDF because the calculator is just going to spit out the p-value. But if we were in a situation where we only had that standardized test statistic, that z or t score, we can use z or t-CDF, right, in the same kind of way. So the other question, the next question, said, what if your t-score is negative 2.5? It said it was a test for a statistical difference, which tells us the alternative is not equal to, n still 50. So I think now's a good opportunity to pause the video and try to find the p-value yourself. And in class, hopefully we'd see this done 2 different ways. So some people mark negative 2.5 for our t-score and shade over here, but this is a 2-tailed test. So one option might be t-CDF, negative infinity, negative 2.5, and then our degrees of freedom, right? So lower, upper degrees of freedom, and that's 49. And then we're going to multiply that answer by 2 because of a 2-tailed test. Hopefully, if we were in class, I'd see some other people who use the same idea, but instead focus on this centerpiece and maybe do t-CDF, negative 2.5, positive 2.5, 49. That would give me this green area in the middle, and then subtract from 1. Whichever way, right? Same idea. So again, like the last video, a major takeaway that I want you guys to have is that this is like really, really similar to everything we've been doing. It's just, hey, now instead of use normal CDF, use t-CDF, but like the idea, the concept, right, is the same. And if we do that, we're going to get our p-value of 0.016. Hopefully that's what you got. And then you can think about it, you reject or fail to reject the null and all that good stuff. All right, so here we go, almost done. Last thing we want to look at, or last thing I want to bring up, I think, yep. So when you go to your calculator, when you go to stat tests, we want to talk about what's going on with, what's the difference between these? What's the difference between like these? And right, same thing down here. For the AP exam, proportions, percents, categorical data, it's always 1-prop, 2-prop Z. For the sake of the AP exam, if it's means quantitative data, it's T. So in AP stats, we are never ever going to use the z-test, the 2-sample z-test, the z-interval, the 2-sample z-interval. It would be easy to use them though, and here's the difference. So there are, in real life, there are z-tests for means. So means could be a z-test with a normal model or a t-test based on the t-distribution, right? And that's not going to happen on the exam. For the exam, we just need to know when would you use either. And so here's the deal. Again, z and t tests or 2-sample z and t tests intervals, right? Those are both used for means. So the t-distribution is what we use if we don't have sigma. So if we don't know the population standard deviation, then we're going to use the t-distribution. That's what's going to happen most of the time. Like if we knew the population standard deviation, then we'd probably know the population mean. And if we know the population mean, we don't need a t-interval or a t-test, right? Because we just like have that number. I don't need to estimate the population mean if I have it. So this is like, to me, like the much more realistic, and this is much more common for what we're going to see in our class. So when you just have a sample standard deviation, that's when you use our T stuff. And this is what's going to happen over the next 2 weeks in our class. Theoretically, though, if you did know the value of sigma, if you did have the population standard deviation, then for means, you would use what's called the z-tester interval or the 2-sample z-tester interval. This, although real in real life, is not going to happen in our class. If it did, it wouldn't be a big deal. You would just see when you went to like, if you go to T interval, it asks for SX. If you go to Z interval, it asks for sigma X, like no big deal. So for us, we just have to know when to use Z-test for means, the bottom of the screen, if you know sigma, when to use T-test for means, the top of the screen when you don't know sigma, and that's going to be the much more common occurrence. So that's it. That's what's up with the t-distribution. Make sure you guys get your assignment done for today. It'll focus on some of this p-value, critical value stuff. Tomorrow, who cares about tomorrow for now? Just do what you got to do and have a wonderful afternoon. I always do that, and then I got to come back here and make it weird at the end.